Something hiding at the edge of the universe just broke our script for how everything began. James Webb pointed into almost pure darkness and found a tiny, furious mystery that has no business existing that early. If you think you know the story of the Big Bang and what came next, stay right here, because that timeline is about to snap. The light that started this whole story left a tiny object we now call MUMZ-14 when the universe was only about 280 million years old. Today the universe is about 13.8 billion years old, so you're hearing about a time when everything was at roughly 2% of its current age. Back then there were no planets like Earth, no Sun, no Milky Way as we know it, just a rapidly changing young cosmos where the first serious structures were switching on. That light has been travelling for about 13.5 billion years before it hit James Webb's mirror. Year after year, galaxy after galaxy formed and evolved, while those photons just kept going, crossing expanding space, never stopping, never slowing, until they finally landed in a detector that turned them into data, then into a spectrum, then into a redshift, and now into the words you're hearing. Here's the twist that doesn't feel natural at all, that travel time does not equal the current distance. Because space has been stretching while the light was in flight, the present-day distance to MUMZ-14 is not 13.5 billion light-years, it's more like 33.8 billion light-years in what we call proper distance. The universe grew underneath that beam of light, so when you look at MUMZ-14, you're not just seeing far away, you're seeing far back in time, and you're looking across a universe that changed size while the signal was on the way. So if we can't fly there, and we can't drop a ruler across 30 plus billion light years, how do we actually know any of this is real and not just a nice looking number on a plot? How do you measure the distance to something you will never visit? The answer is, you don't measure the galaxy itself, you measure what happened to its light. The key tool here is redshift, and it's the universe's built-in ruler and clock. When MUMZ-14 stars were burning, they were throwing out a lot of high-energy, short-wavelength light, especially in the far ultraviolet. As this light crossed space, the space itself expanded. When space stretches, the wavelength of light stretches with it. The light gets redder, meaning it shifts to longer wavelengths. We call the amount of that shift the redshift, and for MUMZ-14 the number is around 14.44. That number tells you how extreme the stretching is. A redshift of 1 would mean the wavelength doubled. A redshift of 14.44 means the wavelengths have been stretched by more than a factor of 15. Take a photon that left MUMZ-14 as deep violet light at about 400 nanometers, something your eyes could in principle see. By the time it arrives here, that same photon has been dragged out to around 6,000 nanometers and beyond, which is deep in the infrared. Your eyes are blind to it, but James Webb's NIRCam instrument is designed exactly for that range. That's why Hubble struggled with these objects, and Webb can suddenly see them. So from the redshift we get two things at once. First, we know MUMZ-14 lived in a universe that was far more compressed, much smaller than it is today. Second, we can connect that redshift to a time after the Big Bang using our best cosmological model. That's how we get about 280 million years after the Big Bang, and that proper distance of roughly 33.8 billion light-years today. It's not random, it's a chain from wavelength to redshift to age and distance. But once we know when and where it is, we hit the next surprise, what this galaxy actually looks like. With a name like Most Distant Confirmed Galaxy, you might picture something huge and majestic, a baby Milky Way stretching across space. That's not what Webb sees. For something that's causing this much trouble in cosmology papers, MUMZ-14 is incredibly small. Its physical size is about 240 light-years across. The Milky Way is about 100,000 light-years wide. That means MUMZ-14 is smaller by a factor of more than 400. If you think in Earth terms, if the Milky Way was spread across the whole width of the continental United States, roughly 4,500 kilometers, or about 2,800 miles, MUMZ-14 would be like a single city dropped somewhere in the middle of that map. Not a continent, not a country, just one dense urban zone in a huge dark landscape. In Webb's images, this doesn't show up as a sprawling spiral with arms. It's a tiny resolved blob, slightly extended point of light. To detect its size at all, astronomers have to model how sharp the telescope's vision is, remove that effect, and see that there is a real but tiny extension left over. It is barely bigger than some of the massive star clusters we see in nearby galaxies today. We are right at the edge of what the telescope can separate. So you'd expect something that compact and that early to be faint, quiet, struggling to form a few stars here and there, right? At this point in the universe, that was the comfortable picture. Lots of small, dim proto-galaxies just starting to get going. This is where MUM-Z14 stops being just interesting and starts being a problem. For its small size, it is absurdly bright, especially in ultraviolet. Astronomers describe its intrinsic ultraviolet brightness using a scale called absolute magnitude, and for MUM-Z14 that value is around -20.2. You don't need to learn the whole system, you just need the bottom line. That level of UV brightness means the galaxy is pumping out roughly 1 billion times the UV light of our Sun. And remember, this is coming from a region only about 240 light-years wide. You're not looking at a gentle, slow-burning dwarf, you're looking at a compact star-forming engine running very close to its limits. Gas in this tiny volume is collapsing into new stars at a high rate. Those stars are blasting intense radiation, and they were doing it only a couple 100 million years after the Big Bang. On a cosmic timeline, that is extremely fast. From that UV output, you can estimate a star formation rate of several solar masses per year. In plain language, that means every year, MUM-Z14 is turning gas with the mass of several suns, each about 2 × 10⁻30 kilograms, into new stars. And it's doing that inside a region that, compared to the Milky Way, is absolutely tiny. High output, tiny volume, very early time, all stacked together. Before James Webb, our best simulation said that at this epoch you'd mostly see small, faint galaxies, often too dim to pick up even with a powerful space telescope. The idea was that the first structures grow slowly, assemble mass step by step, and take time to become bright and chemically rich. You'd catch them in their awkward phase, messy and underpowered. Instead, MUM-Z14 turns up as bright, compact, and already showing signs of chemical enrichment. Heavy elements like nitrogen and carbon are present, which means at least one previous generation of massive stars has already lived and exploded to seed the gas. All of that has happened by 280 million years after the Big Bang. That timeline is much tighter than many models were expecting. It's like skipping several steps in the growth chart and going straight to a surprisingly mature phase. So here is the real tension. If galaxies like MUM-Z14 exist this early, this bright, this enriched, how many of our assumptions about early galaxy growth, star formation efficiency, and feedback are underestimating what the universe can do in its first few 100 million years? And how many more of these shouldn't exist systems are already hiding in Webb's images, waiting for their spectra to be measured and their redshifts confirmed? How can one tiny galaxy be both 13.5 billion years in the past and more than 30 billion light years away at the same time? And how does that even make sense as a real distance you can trust? When you hear that MUM-Z14's light has been travelling for about 13.5 billion years, you're hearing what astronomers call the look-back time. That's literally how long those photons have been in flight before hitting James Webb. So in time terms, you are connected straight back to a moment when the universe was only a few 100 million years old. But if you freeze the universe right now and ask, in this moment, how far away is that galaxy today, you get a different number. Because while the light was travelling, space itself was stretching. The fabric between us and MUM-Z14 got pulled out. When cosmologists run that through the standard cosmology model, the present-day distance to MUM-Z14 comes out to roughly 33.8 billion light-years. So you have two distances that sound like they should match, but don't. The light travel distance, 13.5 billion light-years of journey time. The proper distance today, about 33.8 billion light-years of actual separation in this moment. Both are correct, they just answer different questions. One is, how long has the light been on the road? The other is, how far apart are we now after the road itself stretched under it? To feel how large that is, translate it into kilometres. 1 light year is about 9.46 trillion kilometres, roughly 5.88 trillion miles. Multiply that by around 33.8 billion, and you get on the order of 3 times 10 to the power of 23 kilometres. That is a 3 followed by 23 zeros. You're well beyond any normal instinct here. You can say more than all the grains of sand on Earth, and still not really capture it. But that's the scale you're dealing with when you talk about the distance to Mumsib-14 today. So if we're looking that far back, that deep into time, what does 280 million years after the Big Bang actually mean for the universe itself? Right now, the universe is about 13.8 billion years old. When Mumsib-14 was shining the light we're seeing, the universe was roughly 280 million years old. If you take 280 million and divide it by 13.8 billion, you get around 2%. That means you are seeing this galaxy at about 2% of the universe's current age. Put it on a 24-hour clock, because that's something your brain has practiced with. Let the Big Bang be midnight, and now, today, be the next midnight. On that clock, Mumsib-14 shows up about 29 minutes after the first midnight. Less than half an hour into the day, the universe already has a compact, bright galaxy forming stars like crazy. By that point, there are already dense clumps of gas collapsing into stars. There are regions with heavy elements like carbon and nitrogen, and there is a strong radiation field blasting out into the surrounding hydrogen. That is not a calm, empty universe. It's already busy. Many of our older models were more comfortable with that kind of complexity appearing a bit later, not that close to the start. Mumsib-14 is basically a data point saying, no, things got serious fast. If it's that far away and that early, the next natural question is, doesn't that mean it's moving away from us faster than the speed of light? And doesn't that break the rules of physics? At these extreme distances, the recession speed you calculate from cosmic expansion really does go beyond the speed of light. But that does not mean Mumsib-14 is shooting through space faster than 300,000 kilometers per second, or about 186,000 miles per second. Locally, nothing is allowed to move through space faster than that. That's still the hard limit in Einstein's relativity. What changes is what you mean by moving. In cosmology, very distant galaxies are mostly not flying through space at insane speeds. Instead, space itself is expanding. The distance between us and them increases because more space appears in between. In general relativity, there is no law that says space itself cannot expand so fast. The speed limit applies to objects in space, not to the growth rate of the metric that defines distance. So for Mumsib-14, the comoving recession speed, and the speed you get when you take the expansion rate and multiply by the distance, can absolutely be greater than the speed of light. That sounds like a word trick, but it's a key point. Locally in its own neighbourhood, Mumsib-14 is not ripping through its local space at superluminal speeds. It's sitting in its own region, bound by its own gravity, while the larger scale universe expands and stretches the distance between that region and us. Okay, so you have this massive redshift number, 14.44, and this expanding space picture. How exactly does that turn into a clock that tells you this was 280 million years after the Big Bang, and how small the universe was back then? Cosmologists use a quantity called the scale factor, which you can think of as how big the universe is at some time compared to now. Today, by definition, that factor is 1. At earlier times, it's less than 1. The connection to redshift is straightforward in words. The redshift tells you by what factor wavelengths have been stretched, and that stretching factor matches how much the universe has expanded since the light was emitted. For Mumsib-14, a redshift of about 14.44 means the universe has grown by about 15.44 times in linear size since that light was emitted. Flip that around, and you get that the universe back then was only about 1 divided by 15.44 of its current size. That's roughly 6.5%. So in linear distance, everything was shrunk to about 1/15th. If you take a chunk of space that is 1 million light years across back then, that same region today would span about 15 million light years. Every large-scale distance has been dragged out by that factor. MUMS 14 is sitting way out on that stretched grid. The redshift doesn't just say this light is redder, it tells you this was a much smaller universe, and here is by how much. So now you have the timing, the distance, and the amount of stretching. Why does that particular combination make theorists so uncomfortable? To have a galaxy this bright, this compact, and this chemically enriched only 280 million years after the Big Bang, you need a lot to happen very quickly. First, you need a dark matter halo, the invisible mass that provides the gravitational well, to assemble fast. That halo has to reach hundreds of millions to maybe a billion solar masses in a very short time. Then inside that halo, gas has to cool, collapse, and form stars with very high efficiency. You need star formation rates that are not just on, but in overdrive. You also need at least one round of massive stars to live and explode and pollute the gas with heavier elements, before the stars we are now seeing turn on. That all has to fit into just a couple 100 million years of cosmic history. State-of-the-art simulations before James Webb often struggled to produce many objects like that so early. They could get some bright galaxies, but not in the numbers and with the properties Webb is now hinting at. MUMS 14 is one of the cleanest examples so far that says either gravity in the early universe built up structures faster in the real cosmos than in our simulations, or our recipes for how gas turns into stars and how feedback from those stars shuts things down are missing something important. So the tension is simple to say. Either the universe is better than expected at building bright galaxies early, or our understanding of the physics that controls that build-up is incomplete in a serious way. And if that much is already off at 280 million years, what else are we going to find as we push even closer to the Big Bang? Next comes the obvious follow-up. With distances this insane and signals this faint, how did James Webb actually pick MUMZ14 out of the sky and prove it's real, and not just some closer galaxy pretending to be ancient? So how do you actually pick out one baby galaxy like MUMZ14 from a sky full of faint smudges, and how do you know it's really from 280 million years after the Big Bang instead of something much closer faking it? The first step is brutally simple. You look for something that disappears. Astronomers use James Webb's NIRCam, which has multiple filters, each one sensitive to a different slice of wavelength. When they looked at this field, they saw one object that was just gone in the shorter wavelength filters like F090W, F115W, F150W, and then clearly present in the redder, longer wavelength filters. That pattern is what they call a Lyman-break dropout. The idea is this. In the early universe, there is a lot of neutral hydrogen gas between galaxies. That gas is very good at absorbing photons that are more energetic than a certain threshold, the Lyman limit. So any light from a young galaxy that starts out bluer than that limit gets cut off. You end up with a spectrum that is bright on the red side and then suddenly drops to almost zero on the blue side. Now, because the universe has expanded so much since MUMZ14 emitted that light, that whole cutoff has been shifted into the infrared. The sharp drop, the Lyman-break, no longer sits in the ultraviolet, it has slid into the range where NIRCam is watching. So if you scan across filters, you see this pattern. In the bluer filters, nothing. The galaxy has dropped out. In the redder filters, it appears that is the first red flag that says this could be an extremely high redshift galaxy, but could be is not enough. Color-based selection is messy. Dusty galaxies that are much closer can also look red and faint in the blue filters. They can mimic that dropout behavior without actually being from the early universe. So at this stage, you just have a candidate with a photometric redshift, best guess at its distance based on its brightness in each filter. It's like saying, based on the colors alone, this thing looks like it's at Z around 14, but you cannot treat that as a solid measurement. So the next question is obvious. How do you move from that kind of sketchy color guess to something precise and trustworthy? That's where NIRSpec comes in, Webb's near-infrared spectrograph. Instead of taking a picture through a filter, NIRSpec spreads the galaxy's light out into a spectrum. In this case, they use the prism mode, which gives a low resolution but very broad coverage spectrum, perfect for extremely faint distant targets. Once you have the spectrum, you can watch where that Lyman-break actually lands in wavelength. You're no longer just saying it vanishes here and reappears there. You're measuring the exact point where the flux drops. That position is set by how much the light has been redshifted, which is set by how much the universe has expanded, which is tied to the galaxy's distance and age. For MUMS F14, the measured break pins the redshift at about 14.44, with an uncertainty of plus or minus 0.02. That's a very tight error bar for something this far away. At that point, you're not dealing with a vague impression, you're dealing with a number. So what exactly is this break physically? Neutral hydrogen atoms that still have their electrons, can absorb photons above a certain energy, a bit over 10 electron volts, corresponding to transitions in what's called the Lyman series. Light with higher energy than that threshold gets eaten, light with lower energy passes through. In the frame of the galaxy, that means no photons above the energy survive the trip through the gas around and between galaxies. When that light reaches us, it has been redshifted, but the cut still exists. At MUMS E14's redshift, that suppression line has moved into NIRSpec's observing range. So in the spectrum you see a clear shape. On the red side of the break there is measurable signal, a kind of bumpy continuum. On the blue side the flux falls to almost zero. It really does look like a cliff. That cliff is the timestamp. It tells you where in wavelength the universe drew a line and said, no photons with higher energy get through. Once you've nailed that cliff, you already have strong evidence that this thing is truly at extreme redshift. But the team didn't stop there. NIRSpec also reveals emission lines, narrow spikes on top of the continuum coming from gas in the galaxy itself. For MUMS E14, the spectrum shows about 5 distinct ultraviolet emission lines in the galaxy's rest frame, each detected at roughly 3 times the noise level. That is not super high resolution, but it's enough to be confident they are real features, not random noise. Those lines come from ionized elements in regions where stars are forming. They trace things like carbon, nitrogen, and other ions in the gas. Their positions in wavelength space line up with what you expect if the galaxy really is at Z around 14.44. Their relative strengths give you clues about the chemical composition, the temperature of the gas, and how intense the star formation is. Most importantly, they act as a cross-check. A weird dusty galaxy at much lower redshift would not show that same pattern of lines in those locations. So between the sharp Lyman-break and the set of emission lines, you can rule out the main imposter scenarios. You're not just looking at some nearby galaxy buried in dust, or a fluke noise spike. You're looking at a genuinely distant, genuinely young system. This is where the name of the survey becomes very literal. MUMS E14 was found in a program called Mirage or Miracle, shortened to MOM in the project title, designed specifically to answer an uncomfortable question. Are all these ultra-bright early galaxies that Webb is hinting at real objects, or are they just mirages created by selection effects, noise, and misidentified lower redshift systems? The logic of that survey is, collect high-quality spectra of the most extreme candidates and see how many survive. If most of them turn out to be closer, dusty galaxies, then the earlier claims about a crowded early universe are overblown. If they hold up, then the models are in real trouble. MUMS E14 does more than just hold up. It passes the harshest tests we can throw at it with current instruments. Clean dropout in NARCam, strong Lyman-break in NIRSpec, multiple emission lines consistent with a very high redshift, and properties that match a young, compact, star-forming galaxy in the early universe. That firmly puts it in the miracle category for this survey, not a mirage. And once an object this extreme is confirmed, theorists can't just shrug and say probably a mistake. They now have to explain how a galaxy, This small, this bright and this chemically enriched managed to exist so early in cosmic history without throwing out the rest of cosmology that still works extremely well. So the tension rises again. Now that we know Mum's E14 is real and not a glitch, what does its internal structure actually look like? And how far can you push a tiny galaxy before it tears itself apart with its own star formation? So if Mum's E14 is real, and it's that far away and that early, the next hard question is, what does this thing actually look like up close? And how extreme is it really when you strip away the headlines and just look at the numbers? First, the size. How small can a galaxy be before it starts looking more like a single monster star cluster than a proper galaxy? When astronomers talk about its size, they usually quote something called the effective radius, basically the radius that contains about half of the light. For Mum's E14, that effective radius is around 74 parsecs, which is roughly 240 light-years. That's the scale of the whole system. In kilometres, that is on the order of 2 × 10 to the power of 15 kilometres. Written out, that's a 2 with 15 zeros after it. For a normal human brain, that sounds huge, but in galaxy terms it is tiny. Some massive star clusters in the nearby universe have sizes not much smaller than that. We're talking about objects that, in the local universe, we would happily call just a cluster rather than a full galaxy. Mum's E14 is only slightly bigger than those, but it is being asked to behave like a galaxy, with its own dark matter halo, its own gas reservoir, and its own internal evolution. Compare that with the Milky Way. Our galaxy is about 100,000 light-years across, so if Mum's E14 is about 240 light-years across, you're looking at something more than 400 times smaller in diameter. If you laid the Milky Way out as a big disk, and then dropped Mum's E14 onto it, it would barely register as a small glowing patch in the inner regions. It really is a compact knot of stars, not a grand spiral. With something this physically small nailed down, the obvious follow-up is, what happens when you push star formation this hard into such a tiny volume? How intense does it get on the surface? Once you combine the size with the luminosity, you get a number that really makes theorists sit up. The star formation surface density. That's just the star formation rate divided by the area over which it's happening. For Mum's E14, the area is tiny, so even a moderate total star formation rate turns into an extreme value when you compress it into that footprint. Take a radius of around 120 light-years for a rough half size, and convert that into the usual units astronomers like to use, square kiloparsecs. You end up with an area that is only a few thousandths of a square kiloparsec. Now drop a star formation rate of several solar masses per year into that tiny area. You get many solar masses per year per square kiloparsec. That puts Mum's E14 on the same level as, or even above, the most intense starburst galaxies we see nearby, the ones we already describe as going crazy with star formation. In more everyday language, if you took the entire star formation budget of the Milky Way, all the gas that turns into 1 to 3 suns worth of new stars every year, and forced it to happen inside a region only a few hundred light-years across, you would be in the same regime as Mum's E14. It is not just forming stars, it is doing it in a way that is brutally concentrated. Whenever you see ridiculous brightness and tight concentration, the suspicion kicks in. Is this really starlight? Or is there a supermassive black hole in the middle doing most of the work, like a quasar pretending to be a compact galaxy? For that, you look at the shape of the light, what we call the light profile. If the object were dominated by a bright active galactic nucleus, basically a feeding supermassive black hole, you'd expect something closer to a point source, very strongly concentrated at the centre, almost indistinguishable from a perfect point in the image. Webb's resolution lets you test that. For Mum's E14, the source is actually resolved. That means when you subtract the blurring effect of the telescope's optics, the object still has a measurable size. Its light spreads out in a way that looks more like an extended star-forming region than a single sharp point-like core. That doesn't prove there is no black hole in there at all, There very well could be a growing black hole, maybe with a mass of a few 100,000 or a few million suns. But in the ultraviolet, at least, the data say the bulk of the light is coming from stars and the hot gas around them, not from a quasar blasting everything with X-rays. So you have a compact star-dominated galaxy with extreme surface brightness. With that much action, you'd expect a lot of dust because massive stars live fast, die fast, and their deaths seed the gas with dust grains. So why doesn't MUMZ-14 look choked and reddened? Why does it look so clean? This is where something called the UV slope, often written as beta, comes in. It describes how the brightness changes as you move from shorter to longer ultraviolet wavelengths. For MUMZ-14, beta is around -2.5. In simple terms, that is very blue. A spectrum that blue tells you that there is very little dust blocking or scattering the light. That makes sense in this early universe context. There hasn't been enough time for many generations of stars to live, die, and create large amounts of dust. The heavy elements are there. We see signs of things like nitrogen and carbon, but the dust grains built out of those elements either haven't had time to grow or they are being destroyed almost as fast as they form by intense radiation and shocks. The key point is, we are seeing the raw, mostly unfiltered output of some of the hottest, youngest stars you can get. These are stars with many times the mass of the Sun, surface temperatures tens of thousands of degrees, flooding their surroundings with ultraviolet radiation. There is no thick, dusty curtain in front of them to smooth things out. We are looking almost directly into the furnace. All of that still feels abstract until you stack it up against something you know, your home galaxy. How does MUMZ-14 really compare to the Milky Way? Not in poetry, but in basic numbers. The Milky Way forms on the order of 1 to 3 solar masses of new stars per year, depending on which study you look at. That star formation is spread over a disk tens of thousands of light years across, maybe 50,000 light years in radius, plus some extended regions. So the Milky Way has a moderate star formation rate, but it is diluted over a huge area. The star formation surface density is relatively low. MUMZ-14, by contrast, might be forming a comparable or even higher amount of stellar mass per year, but it is squeezing that into a region only about 240 light-years across. That is the difference. Same or higher output, dramatically smaller area. If you could travel at 1% of the speed of light, about 3,000 kilometers per second, or roughly 1,900 miles per second, you could cross that whole star-forming region in just a few tens of thousands of years. By galactic standards, that is a short walk. In human terms, the situation is brutally compressed. The Milky Way is like an entire country of cities, towns and suburbs all contributing to a moderate total energy bill. MUMZ-14 is like forcing that entire energy bill into a single high-rise block. The energy, the radiation, the feedback from all those massive stars is packed into a tiny space, and that leads straight into the next uncomfortable question. If MUMZ-14 is this compact and this intense, how is its star formation changing over time? And how long can a system like this keep burning at full power before it blows itself apart or runs out of fuel? How fast can a galaxy slam its foot on the gas before it starts to tear itself apart? And is MUMZ-14 already in that danger zone? When astronomers model the spectrum of MUMZ-14, the strength of its ultraviolet lines and the smooth light in between, they can back out not just how many stars it is forming now, but how that rate has changed over time. The surprising result is that in the last roughly 5 million years, its star formation rate seems to have jumped to about 10 times higher than its average over the previous 50 million years. On human scales, 5 million years sounds like forever. On galaxy scales, especially at this early time, 5 million years is very short. That is only a handful of lifetimes for the most massive stars. So going from average to 10 times the average in that window is not a gentle ramp, it is a spike. You go from a busy system to a full-blown starburst in a very short cosmic moment. So the first big point is simple. MUMZ-14 is not just forming stars quickly, it is forming them much faster than it used to, even by its own intense standards. It is in an active burst phase right now, in the light we are seeing. and that means the objects driving its light are not calm, long-lived stars like the Sun, but something much more extreme. How do we know the stars themselves are that young and that massive, and not just an older population shining steadily in the background? This is where something called equivalent width comes in. When you look at the spectrum, you see bright, narrow emission lines sitting on top of a continuum. The equivalent width is a way of measuring how strong each line is compared to that underlying baseline. For MUMZID-14, the rest frame ultraviolet lines have equivalent widths of about 15 to 35 angstroms. Numbers by themselves are boring, so here is what that means. Lines that strong in the ultraviolet typically need a lot of very hot, very young, very massive stars. These are stars with many times the Sun's mass, sometimes dozens of times, with temperatures and radiation fields far above what our star puts out. They live fast and die fast, burning through their nuclear fuel in just a few million years before collapsing or exploding. So when you see those 15 to 35 angstrom equivalent widths, what you're really seeing is the signature of a fresh, top-heavy population of stars blasting ionizing radiation into the surrounding gas. It's like a fingerprint that says, this light is coming from a crowd of massive, short-lived stars, not an old, quiet stellar population. Now, you can look at the total ultraviolet luminosity, the total UV light this galaxy is emitting, and use a standard conversion to turn that into a star formation rate. Astronomers have calibrated that relationship by looking at many galaxies where they can measure both. For a dust-free galaxy, a given ultraviolet output corresponds to a certain rate of turning gas into stars. For MUMZID-14, plugging in the observed UV brightness gives you a star formation rate of a few solar masses per year. That might not sound huge until you remember how small this galaxy is and how early we're catching it. In simple terms, every year, this tiny object turns gas equivalent to several suns into new stars. Each sun has a mass of about 2 times 10 to the power of 30 kilograms. So that is several times 2 times 10 to the power of 30 kilograms of gas per year, turning into stellar cores. If you break that down even further, you're talking about converting on the order of hundreds of Earth masses of gas every single second into new stars. Earth's mass is about 6 times 10 to the power of 24 kilograms. MUMZID-14 is taking that kind of mass and gas, again and again, every second, and locking it into stars. For something only about 240 light-years across, that is an absurd level of activity. The next obvious question is, where does all that gas come from? And how does such a small object keep that level of star formation going without simply running dry in no time? To sustain this, MUMZID-14 cannot just be a little puff of gas on its own. It has to be sitting inside a dark matter halo, a big invisible ball of mass whose gravity can hold onto gas and keep pulling fresh material in. Based on its brightness and inferred stellar mass, models suggest the halo mass is in the range of hundreds of millions to maybe a few billion times the mass of the Sun. Halos like that at a redshift of about 14 are rare, but not impossible in the standard cosmology model. They form in what are called high sigma peaks, regions where the initial density fluctuations in the early universe started out above average. In those special regions, gravity wins earlier and faster, and matter collapses into massive halos sooner than in quieter areas. So the picture is that MUMZID-14 lives in one of these overachiever neighbourhoods, a part of the early universe where things just grew faster. Cold gas from the cosmic web, from filaments of matter that stretch over millions of light years, is flowing into this tiny central halo, feeding the ongoing starburst. The galaxy we see is just the bright central knot of a larger dark matter structure. But even with a steady gas supply, there is a limit to how long a system this compact can keep behaving like this. When you pack that many massive stars into a small volume, you also pack in the feedback, the energy they dump back into their surroundings. Massive stars drive powerful stellar winds while they are alive, fast flows of particles leaving their surfaces at thousands of kilometers per second. At the end of their lives, many of them explode as supernovae, releasing huge amounts of energy into the surrounding gas. In a system as small as MUMZID-14, those shocks do not have to travel very far before they start to matter. Over time, those winds and explosions will heat and push the gas around, and some of it will be blown out of the shallow gravitational well of the galaxy altogether. That process shuts down or at least throttles future star formation. The system can go into a burst and pause cycle, a big spike of activity, followed by a quieter phase while things cool and resettle, then maybe another burst later if more gas flows in. So Mumsy 14 is likely caught in a short, intense phase of its life. Right now, in the light we see, it is in a rising or peak starburst, with a recent star formation rate about 10 times higher than its longer-term average. But it cannot keep that exact pace forever without burning through or blowing out its fuel. That leads directly to the next tension. If this galaxy is already in a burst phase, already chemically enriched, and already dumping huge energy into its surroundings at just 280 million years after the Big Bang, what does its chemical fingerprint actually look like? And what does that tell us about the kinds of stars that lived and died there before the ones we are seeing now? How do you end up with a baby galaxy that already looks chemically old? And why does that freak cosmologists out more than the distance or the brightness? When you split the light from Mumsy 14 into a spectrum, you don't just see hydrogen and helium, you see signs of heavier elements like nitrogen and carbon in its gas. That detail alone is a big deal. In the very early universe, right after the Big Bang, you basically only have hydrogen, helium, and a tiny bit of lithium. Everything heavier, carbon, nitrogen, oxygen, iron, has to be made inside stars and then thrown back into space when those stars die. So if you're seeing nitrogen and carbon in Mumsy 14 at 280 million years after the Big Bang, that means this galaxy is already on at least its second round of star formation. One generation of massive stars has already formed, lived out their short lives, exploded or shed their outer layers, and polluted the gas with those heavier elements. Then a new generation of stars formed out of that enriched gas, and those are the ones lighting up the spectrum we see now. In the standard story, you expect that kind of chemical layering to take more time. You don't necessarily expect a compact galaxy at this early stage to already show clear signatures of elements like nitrogen at noticeable levels. That's supposed to be a later development, after more cycles. Mumsy 14 is telling you, no, that process kicked in fast. And it's not just that nitrogen and carbon are present. The ratio between them is strange. The data suggest a high nitrogen to carbon ratio, what astronomers shorten to high N over C. That means, compared to carbon, there is more nitrogen than you'd comfortably expect from standard stellar evolution models at this stage. Even in nearby galaxies today, that kind of elevated nitrogen compared to carbon is not common. You see it in some very specific environments, like certain ancient globular clusters in the Milky Way or in a small fraction of ultra-metal-poor stars in our galaxy's halo. Those are objects we already think of as fossils from very early times. So when you see a similar nitrogen pattern in Mumsy 14, almost at cosmic dawn, you are suddenly connecting two very different data sets, weird old stars here, and a tiny blazing galaxy out there. That match in abundance pattern is what really hurts the models. Our usual recipes for how normal massive stars make carbon and nitrogen then mix and eject them don't easily give you such a high nitrogen to carbon ratio this early. So people start asking, okay, what kind of stars do you need to get this chemistry so fast? One idea is that the early universe, especially in these dense compact systems, might have been able to form supermassive stars, not just 10 or 50 times the mass of the Sun, but hundreds or even thousands of solar masses. These are in a different league from the massive stars we usually talk about. Inside those monsters, the conditions are extreme. Their cores and envelopes can mix in different ways, their rotation can stir material around, and the fusion chains they run through can produce a lot of nitrogen relative to other elements. When these stars die, whether they collapse, explode, or shed their mass in violent winds, they dump that nitrogen-rich material into the surrounding gas. So one working picture is, in the cramped high-pressure environment of Mumsy 14, gas collapses into a very dense cluster. Supermassive stars form, they live short, intense lives, and then they enrich the gas with a weird, nitrogen-heavy chemical cocktail. Then the normal massive stars we're seeing now form out of that already processed gas. MUMS-ID14 may be catching that whole process in action, not as a theory but as data. This is where the link back to the Milky Way becomes powerful. In our galaxy, astronomers have found some of the oldest stars in globular clusters and in the halo, with similarly strange nitrogen enhancements. For a long time, those stars have been treated like fossils with unclear backstories. The chemistry says something odd happened where I formed, but we don't get to see that environment anymore. It's gone. MUMS-14 gives you something close to real-time footage of that kind of environment in the early universe. You have the same sort of chemical signal, high nitrogen relative to carbon, but now you can anchor it to an actual galaxy, with a size, a redshift, a star formation rate, and a place in cosmic history. It's like finding a weird pattern in old bones in your backyard, and then discovering a living ecosystem on the other side of the planet that leaves the same pattern in fresh bones. Suddenly, the fossil record and the live environment connect. There's another twist in the data that adds to the puzzle. The ultraviolet slope of MUMS-E14 is very blue, with that beta value around -2.5. That tells you there is very little dust blocking or reddening the light. So on the one hand, the gas is chemically enriched, there are definitely heavy elements present. On the other hand, the amount of dust seems extremely low. Normally, in nearby galaxies where you have a lot of metals, you also have a lot of dust. Dust grains are built out of those heavy elements, so metals and dust tend to grow together over time. MUMS-ID14 breaks that link. The metals are there, but the dust is not. That points to a very specific physical regime. There has been enough star formation to enrich the gas chemically, but not enough time, or not the right conditions, for large amounts of dust to build up and survive. Dust grains may still be small, rare, or constantly being destroyed by the intense radiation and frequent shocks from supernovae and stellar winds. So you end up with a chemically evolved but dust-poor system. The gas has been processed, but the medium is still clean from a dust point of view. That combination is hard to study in the local universe, because nearby galaxies with high metallicity usually also have plenty of dust. MUMS-14 gives you a clean view into a phase where heavy elements have appeared, but dust physics hasn't fully caught up yet. So you have a compact galaxy, already enriched with nitrogen and carbon by 280 million years, showing a weird nitrogen boost, possibly shaped by supermassive stars with almost no dust in the way. The obvious next question is, if a galaxy like this is already chemically busy and blasting out ionizing radiation this early, what is it doing to the hydrogen fog that filled the universe at that time, and how much is it helping to clear that fog and turn the universe transparent? How do you clear an entire universe full of hydrogen fog fast enough for light to travel freely, and is MUMS-E14 one of the engines doing that job way earlier than we planned for? Right after the Big Bang, once things cooled down enough, protons and electrons combined to form neutral hydrogen. That phase is called recombination. After that, the universe was filled with this neutral hydrogen gas. For ultraviolet light, neutral hydrogen is basically a fog. It absorbs high-energy photons very efficiently. So even when the first stars and galaxies started to form, their light didn't just stream out into a perfectly transparent universe. It hit this sea of neutral hydrogen. Only when enough high-energy photons with energies above about 13.6 electron volts, enough to knock electrons off hydrogen atoms, started pouring out did they begin to carve out clearings. Those clearings are ionized bubbles, regions where the gas is no longer neutral. The era when the universe transitions from mostly neutral hydrogen to mostly ionized hydrogen is called reionization. It's a key chapter. Before reionization, the universe is mostly opaque to strong UV. After reionization, light from galaxies and quasars can travel much more freely across space. At the redshift of MUMS-E14, around 14.44, a lot of models say the universe should still be almost completely neutral. We're very close to the start of reionization here, so you would expect light from a galaxy like this to show clear signs of passing through a lot of neutral hydrogen. One of those signs is something called a damping wing in the spectrum. If there is a lot of neutral hydrogen along the line of sight, it doesn't just cut off photons sharply at a single wavelength. It smears that absorption out a bit, making the drop in flux more gradual on the blue side of the Lyman-break. That extended wing is a telltale signature of a highly neutral intergalactic medium. But when astronomers look at the spectrum of MUMS E14, that damping wing is not very strong. The Lyman-break is there, but the extra smoothing you would expect from a universe that is almost 100% neutral isn't obvious. That is surprising at this redshift. It hints that at least around MUMS E14, the hydrogen is already significantly ionized by the time the light leaves. So then you have to ask, is MUMS E14 just lucky, sitting behind some already cleared patch, or is it actually one of the things doing the clearing? Given its ultraviolet luminosity and intense star formation rate, MUMS E14 is producing a huge number of ionizing photons. Each of those photons has energy above 13.6 electron volts, enough to strip an electron off a hydrogen atom. Estimates from models say this galaxy could be throwing out something like 10 to the power of 54 to 10 to the power of 55 ionizing photons every second. In a tiny compact system like this, that flood of radiation doesn't stay local. It pushes out into the surrounding gas and starts carving a bubble, an ionized region where hydrogen atoms have been broken apart into protons and electrons. That bubble can grow to tens of thousands of light years across, possibly more, depending on how long the burst lasts and how quickly new gas flows in to replace what's been ionized. So MUMS E14 is not just a passive light bulb sitting in the fog. It is actively eating away at that fog in its neighborhood. It is reshaping its local patch of space, turning a neutral region into an ionized one. Now, if galaxies like MUMS E14 were extremely rare, just a few freak objects in the whole universe, this would be an interesting detail but not a game changer. But early James Webb surveys are hinting that bright, compact galaxies at high redshift might be far more common than we expected. Some results suggest there could be around 100 times more bright galaxies at these early times than pre-JWST models predicted. If that's even roughly true, then the impact on reionization is big. Instead of a slow, gradual, uniform process, you get something more aggressive and patchy. High-density regions where dark matter halos and galaxies pile up would reionize early and fast. They'd punch holes in the hydrogen fog ahead of schedule. Lower density regions would lag behind, staying neutral longer. So cosmic dawn stops looking like a smooth fade in and more like a universe full of individual bright zones punching out ionized bubbles that grow and overlap. MUMS E14 becomes not just a curiosity, but a prototype of the kind of system that could have driven that process. This is exactly where future radio telescopes come in. Neutral hydrogen emits radiation at a wavelength of 21 centimeters in the radio part of the spectrum. Arrays like the Square Kilometre Array are being built to map that 21 centimeter line across the sky and across different redshifts. What they will see, if everything works, is a kind of map of where the hydrogen fog is still present and where it has been cleared. Neutral regions will glow in 21 centimeters. Ionized regions will show up as holes, as missing signal. MUMS E14 gives a concrete test case. If galaxies like this are already surrounded by ionized bubbles at redshift 14 and beyond, then in 21 centimeter maps you should see small cavities around the positions of objects like MUMS E14, even at very early times. Those holes would confirm that reionization is already well underway in those regions. So now the picture sharpens. You have a compact galaxy, chemically enriched, blasting out vast numbers of ionizing photons, likely sitting in a high-density region, and already carving a clean path through the hydrogen fog at just 280 million years after the Big Bang. The next question is MUMS E14 just one dramatic example, or is it part of a whole population of unexpectedly bright early galaxies that collectively break our old galaxy formation models and force us to rethink how fast structure can grow in the young universe? How big a problem is MUMS E14, really? Is it just one weird object, or is it the visible tip of something much bigger hiding in the data? When the Mirage or Miracle survey team pointed James Webb at the sky, they weren't just looking for a single record breaker. They mapped about 350 square arc minutes of sky. That's roughly like taking the full moon, slicing it into around 40 equal pieces, and using one of those slices as your survey window. It sounds small, but for ultra-deep imaging with Webb, that is a serious patch. In that area, they didn't just find Mum's E14, they found a whole population of bright, high redshift galaxy candidates around redshift 14 to 15. When they turned those detections into a number density, basically how many such galaxies you get per unit volume of the universe, they got something brutal for the old models. The observed number density of bright galaxies at those redshifts is about 182 times larger than what consensus pre-JWST models predicted. Not 10% higher, not double, more than 2 orders of magnitude off. That immediately tells you Mum's E14 is not a total freak. It is extreme, yes, and it's the most secure, spectroscopically confirmed one right now, but it's sitting in a crowd. The iceberg is the whole population of similar objects that the survey hints at. Mum's E14 is just the most carefully measured example we can point to and say, this one, for sure, is real. So how did the old models miss this so badly? What were they assuming about the early universe that gave such low counts? Before Webb, most simulations and semi-analytic models were tuned to match what we saw with Hubble and ground-based telescopes at lower redshifts, like 6, 8, maybe up to around 10. Those models assumed that dark matter halos in the early universe assembled in a fairly gradual way, that gas cooled and settled into those halos over some time, and that the efficiency with which that gas turned into stars stayed modest. On top of that, they assumed feedback from young stars was very effective, even early on. Supernovae and stellar winds were expected to blow a lot of gas back out of small halos, cutting off runaway star formation. You plug all that into a ΛCDM framework, dark energy plus cold dark matter, and you get a universe where bright, massive galaxies at 280 million years after the Big Bang are extremely rare. In many runs, you basically get none at all in a volume the size of the Mirage or Miracle survey. So when Webb looks at a comparable volume and finds not 0 but multiple candidates, and then confirms Mum's E14 sitting right at the top end, the immediate message is, the early universe is better at building bright galaxies than those models allowed. Something in the input physics is underestimating how quickly light can ramp up in the first few 100 million years. This is now putting serious stress on the big simulation suites. If you want to match Webb's counts, you have to start turning knobs. You can make dark matter halos grow faster, for example by assuming more rapid merging or slightly different initial conditions. You can make star formation more efficient at high redshift, so that a larger fraction of the available gas turns into stars in a short time. Or you can make feedback less effective, meaning that when stars explode, they don't blow out as much gas as you thought, letting star formation continue instead of shutting it down. Some high-resolution simulations, like the Renaissance simulations and other similar projects, had already shown that in special regions, you can get rare, massive systems earlier than average. They zoom in on high-density patches and see that, under the right conditions, big halos and bright galaxies are possible. But there's a gap between possible in a small special region and common enough to match what Webb sees over a fairly large area of sky. It's one thing to produce one Mum's E14-like object if you pick a particularly favourable patch. It's another to produce enough of them that your predicted number density lines up with this 182 times boost. Matching both the brightness and the number of these galaxies at once is what remains challenging. That leads to the big question people love to ask: does this mean ΛCDM, the standard cosmological model with dark energy and cold dark matter, is broken? Right now, the honest answer is probably not. ΛCDM sets the overall expansion history and the growth of dark matter structure on large scales. Those parts are still strongly supported by the cosmic microwave background, galaxy clustering, and other probes. What MUMZ14 and its cousins really attack is not the underlying expansion and gravity, but the baryonic physics we plug in on top. The rules for how ordinary gas cools, falls into halos, forms stars, and then gets pushed around by radiation and explosions. So this is less like finding out your calculator is broken, and more like finding out the formula you typed into it is missing a term. The basic framework for how the universe expands can still be right, while our prescriptions for early star formation and feedback are off by a large factor in these extreme environments. But even if ΛCDM survives, something more subtle is definitely dead, and that's the comfortable story we used to tell about early galaxies. For a long time, the standard picture in popular science was, first the universe cools, then a long, slow build-up of small, faint proto-galaxies, mostly invisible to current telescopes, then gradually bigger, brighter systems switch on later. The early stages were thought of as a mostly dark, quiet ramp-up. What Webb and MUMZ14 in particular are showing you instead is a universe where bright, compact, chemically evolved systems show up much earlier, and in much larger numbers than we expected. Tiny galaxies with high star formation surface densities, weird chemical fingerprints, and strong UV output are sitting right up against the observational edge. That forces a shift in attitude. Theories now have to chase the data. You can't just say, our models predict this, therefore the universe must behave that way. Webb is saying, no, this is what the universe actually did, fix your models. The early universe is not a quiet waiting room. It's already busy building complex structures at high speed. And once you accept that, the next question lands hard. If these bright galaxies are growing this fast, this early, what kind of dark matter skeleton are they sitting on top of? And how extreme do their invisible halos have to be to hold all of this together? How much invisible mass do you need under the hood to make a tiny galaxy like MUMZ14 this bright, this early? And what does that say about the skeleton of the universe itself? Everything you see in MUMZ14, the stars, the gas, the radiation, is just the tip of the iceberg. All of it is sitting inside a dark matter halo, an invisible blob of mass whose gravity keeps the whole system together. At a redshift around 14, the estimates for that halo's mass land in the range of about 1 billion to 10 billion solar masses. In kilograms, that's up to roughly 2 times 10 to the power of 40 kilograms of mostly invisible matter, setting the stage for a 240 light-year-wide starburst. For this point in time, only 280 million years after the Big Bang, that is a huge structure. You're not talking about a tiny random lump, you're talking about one of the earliest heavyweights in the young universe already deep enough in its gravity well to trap and compress gas into a furious star-forming core. So the obvious follow-up is, how do you even build a halo that big in such a short time, starting from tiny fluctuations in the early universe? In the standard ΛCDM picture, small density fluctuations in the early universe grow under gravity. Places that start off slightly denser than average slowly attract more matter and become even denser. Over time, those patches collapse into dark matter halos. Most regions grow at a normal pace, but you also get rare regions where the initial fluctuation is several standard deviations above the mean, what cosmologists call high sigma peaks. Those are the places where big halos can form early. ΛCDM can produce halos in the mass range needed for MUMZ14 by 280 million years, but they're supposed to be rare. Now, when you line that up with the Webb counts, where you're seeing not just one but many bright galaxies at these redshifts, you start to wonder if we are seeing more of these high sigma peaks than our models assumed, or if the initial conditions we fed into some simulations weren't capturing the full tale of the distribution. It's like running a city building simulation where you expect mostly low-rise buildings with a few skyscrapers, and then looking at the real data and finding way more skyscrapers than allowed by your rules. The base theory says skyscrapers are possible. The tension is about how many you actually get. Once you have that dark matter halo in place, the next key quantity is how efficiently the normal matter, the bryons, meaning gas, inside that halo gets turned into stars. MUMZ14's brightness gives you a handle on that. From the UV output, the spectrum, you can estimate its stellar mass, which likely sits at a few times 10 to the power of 7 to 10 to the power of 8 solar masses. If the halo mass is around 10 to the power of 9 solar masses and the stellar mass is in that few times 10 to the power of 7 to 10 to the power of 8 range, then several percent of the baryons in that halo have already been locked into stars. That might sound like a small fraction, but for this epoch, and for such a compact system, it's high. Many older models expected lower conversion efficiencies this early, because feedback from young stars and supernovae was supposed to blow gas back out and keep star formation more modest. MUMSIF-14 is saying no, at least in some halos, the pipeline from gas to stars is very efficient very early. The halo is not just big, it is using its gas aggressively. That naturally raises the question people love to jump to. Does this mean the dark matter itself has to be something exotic and different from the standard cold dark matter picture? Right now, MUMSIF-14 alone cannot give you a clean yes or no on that. Some alternative dark matter models, like warm dark matter, tend to suppress the formation of small halos and delay the growth of large structures. In those scenarios, getting big halos by 280 million years is harder. So MUMSIF-14 type objects are more of a headache. Self-interacting dark matter models can also change how halos grow and merge, but the current data are not sharp enough to say this rules out warm dark matter, or this forces self-interacting dark matter. What MUMSIF-14 does say clearly is that if dark matter is the standard cold kind, then the way we handle galaxy formation physics on top of that needs serious tuning. The problem is not the existence of dark matter halos, it's how quickly and efficiently those halos can light up with stars. So instead of dark matter must be different, the current, more honest statement is galaxy formation in high redshift halos is more aggressive than we thought, and we have to adjust the recipes we plug into our simulations. The dark sector might still be standard. The visible sector's behaviour is what's surprising us. Zooming out one step more, you can ask, where does MUMSIF-14 sit in the larger structure of the universe? Is it just a lone dot, or does it trace something bigger? In the cosmic web picture, dark matter and gas don't distribute randomly. They form a network of filaments and nodes. The nodes are where filaments intersect and where the largest halos live. That's where you expect to find early bright galaxies like MUMSIF-14. From those nodes, filaments of gas and dark matter stretch for millions of light years, acting like highways that funnel material inward. MUMSIF-14 should be at one of these nodes connected to that web. Gas flows along those filaments into the halo, feeding its star formation. Smaller companion halos, maybe hosting fainter galaxies, should also be orbiting or falling in along these same structures. Right now we're mostly seeing the brightest knot at the centre, but deeper imaging and spectroscopy around MUMSIF-14 can look for those companions and filaments directly. If future surveys map out a group of galaxies and extended structure around MUMSIF-14, they won't just be confirming one object, they'll be watching a patch of the early cosmic web form in real time. That would tie the story together. A rare massive halo at a node of the web, over-efficient at turning gas into stars, lighting up the reionization era from the inside. And once you see MUMSIF-14 as a dense knot in that web, another idea pops up. Could objects this compact actually be the ancestors of the dense star clusters we see orbiting the Milky Way today? And are we watching the early stages of those clusters being built inside this tiny galaxy? How small does a galaxy have to be before you seriously have to ask if you're actually looking at the birthplace of massive star clusters instead? We already said MUMSIF-14 is only about 240 light years across. That size is not far off from some of the most massive globular clusters we see around the Milky Way today. Globular clusters are those dense balls of old stars, usually a few tens of light years across, packed with hundreds of thousands to millions of stars. MUMSIF-14 is bigger than a typical cluster, but not by orders of magnitude. It sits in the same basic size range. The difference is brightness. MUMSIF-14 is far brighter than any single globular cluster you see orbiting the Milky Way. So instead of thinking of it as one giant star cluster, A better picture is, Mumsy 14 might be a compact region where many cluster-scale units are forming at once inside a small dark matter halo. It's compact like a cluster, but bright like a galaxy, which is exactly the kind of thing you'd expect if you're catching multiple cluster-forming sites in their youth, still blended together. So then you line up the chemistry. Does the chemical fingerprint match that picture, or does it look more like a normal young galaxy? This is where the nitrogen pattern jumps out again. Some of the oldest globular clusters in the Milky Way show strange chemical signatures. Certain stars inside them have enhanced nitrogen compared to carbon and other elements. That is already a long-standing puzzle in stellar astrophysics. Something in their birth environment produced a lot of nitrogen and then locked it into later generations of stars. Mumsy 14 shows a similar kind of nitrogen enhancement relative to carbon in its gas. That means the stars forming there now are being born in material that has already been processed in a way that favours nitrogen. When you see the same kind of pattern in an ultra-early galaxy, and in some of the oldest clusters in our own halo, the simple reading is the same type of enrichment channel might be operating in both places. One leading idea for how you get that high nitrogen is the presence of supermassive stars in very dense birth environments. Not just massive stars, but supermassive ones, more than 100 times the Sun's mass, maybe even a few hundred or more. The scenario goes like this. In a very dense gas cloud, you form a star cluster with a total stellar mass of maybe a few 100,000 to a million solar masses. That's 10 to the power of 5 to 10 to the power of 6 suns worth of stars. In that crowd, a small number of extremely massive stars form. These supermassive stars live very short, violent lives. Because of their internal structure and strong mixing, they produce a lot of nitrogen in their interiors. As they evolve, they lose mass through intense winds, or they explode, dumping nitrogen-rich material back into the gas inside the cluster. Then a second generation of stars forms from that enriched gas. You're left with a cluster that has at least 2 distinct chemical populations, some stars with more normal composition, and some stars with elevated nitrogen. That matches what we actually see in many globular clusters today. Now zoom back out to Mumsy 14. Instead of one such cluster, imagine several of these dense clouds doing this at the same time inside that 240 light-year region. Each cloud is making of order 10 to the power of 5 to 10 to the power of 6 solar masses of stars, including a few supermassive stars that process and dump nitrogen. The whole system's gas then carries that nitrogen-rich signature. Mumsy 14 becomes a zoomed-out view of many cluster-like units forming and chemically evolving together in a tiny halo. So what happens to those cluster-like knots over the next few 100 million years as the universe keeps evolving and more matter falls in? In the hierarchical growth picture, small structures merge to make bigger ones. Those cluster-scale clumps inside Mumsy 14 are not going to stay in a neat, isolated configuration forever. Gravity will pull them together. Dynamical friction, the drag that massive objects feel as they move through a sea of stars and dark matter, will cause the densest clumps to sink toward the center of the halo. Over time, as more gas flows in from the cosmic web and more stars form, those clumps can merge into a central concentration. You start to build something that looks more like the bulge of a larger galaxy. The original cluster-like units may get smashed together, stripped or buried in the growing central structure. Some may survive as tightly bound clusters orbiting in the outer regions. Others may dissolve into the general stellar population. So Mumsy 14, as we see it, might not be a single smooth ball of stars. It could be several clumps gravitationally tied together, already on their way to merging into a more massive galaxy. Hundreds of millions of years later, a descendant of Mumsy 14 could look like a more familiar-looking galaxy, with a central bulge and some surviving clusters in its halo, and we would never know what those pieces originally looked like. Now connect that to what we actually see around the Milky Way today. When astronomers study ancient stars in the halo and in globular clusters, they're looking at objects that are more than 10 billion years old. Those stars are relics from very early times. Their chemistry, especially the weird nitrogen enhancements in some clusters, suggests they formed in environments with strong early enrichment, exactly the kind of environment we think Mumsy-14 represents. So the punchline is direct. When you look at one of those old globular clusters through a backyard telescope, or when a spectrograph measures the abundances in a metal-poor halo star, you're looking at leftover fragments from systems like Mumsy-14. JWST is finally showing you the before shot, a compact, hyperactive, chemically strange galaxy at redshift 14. The stars around us in the present-day Milky Way are the aftershot, the shrapnel that survived mergers, stripping, and 13 billion years of dynamical evolution. That's how a small, faint yellow dot in a James Webb image at Z around 14 turns into something that directly connects to the old stars over your heads tonight. It's not just an abstract object in a faraway universe. It's part of the family history of the galaxies and clusters we live with now. And once you see that link, there's another question that becomes impossible to avoid. If Mumsy-14 is so early and already looks this complex, can we really call it the first galaxy after the Big Bang? Or are we just seeing the brightest, loudest member of a population that started even earlier, beyond what we can currently detect? So is Mumsy-14 actually the first galaxy after the Big Bang, or are we fooling ourselves with that phrase? Here's the straight answer, and it matters that you hear it clearly. Mumsy-14 is, right now, the most distant confirmed galaxy we've ever seen. Confirmed means we have a solid spectroscopic redshift, not just a colour-based guess. It beats the previous record holder, a galaxy called JADS-GS-Z 14-0 by on the order of 10 to 20 million years in look-back time. That is a tiny difference compared to 13.8 billion years of cosmic history, but it does push the frontier. However, most distant confirmed galaxy we've seen so far is not the same thing as first galaxy in the universe. There is nothing in the data that says this is where galaxy formation started. What it really says is, this is as far as our current instruments and exposure times and techniques have managed to reach. Mumsy-14 is the latest mile marker we've painted on the road, not the place where the road begins. So why does the internet keep calling it the first galaxy after the Big Bang? And why does that phrase feel wrong but still keep popping up in headlines? Part of it is simple selection bias. James Webb is incredibly powerful, but it's still flux limited. That means it only detects objects above a certain brightness. The further away you go, the fainter things look, and below a certain flux level, they just vanish into the noise. So what do we see at the extreme edge? Not the quiet, modest systems. We see the loudest ones. At these redshifts, Webb preferentially picks up the brightest, most actively star-forming galaxies like Mumsy-14, not the first tiny things that ever formed stars. There could easily be huge numbers of smaller, fainter galaxies out there at even higher redshifts beyond 20 that we're simply not picking up yet. Those could be doing a lot of the hard work of reionizing the universe, but we won't know they're there until we have either deeper exposures, lensing help from foreground clusters, or more sensitive future instruments. So when you hear first galaxy, mentally translate it to brightest, most extreme galaxy we can currently confirm at the edge of our reach. It's not a lie, but it's incomplete. Still, even with that caveat, the phrase doesn't come from nowhere. Calling Mumsy-14 the first galaxy after the Big Bang captures something real. It shows that complex, bright systems exist shockingly early. It shrinks the comfortable gap people used to imagine between t equals 0 and the era of mature galaxies. Before Webb, a lot of popular explanations were happy with a story like Big Bang, long dark period, slow build-up, then galaxies. Mumsy-14 forces you to tighten that story. You've got a compact, chemically enriched, high star formation rate system already going hard at 280 million years. So while the literal phrase first galaxy is wrong, the emotional message, wow, galaxies got serious much earlier than we thought, is actually accurate. That's why the headline sticks. It's sloppy in wording but right in tone. So how much earlier could galaxies really start if Mumsy-14 is not the first? In most current models, small dark matter halos can start forming stars as early as 100 to 200 million years after the Big Bang. In some scenarios, the very first star clusters might even appear a bit earlier than that, in the highest density patches. Those first systems wouldn't look like MOMZ-14. They'd be smaller, fainter, or fragile. They might host the very first generation of stars, what we call population 3 stars, massive metal-free stars made from pure hydrogen and helium. Those population 3 stars are where some of the more exotic ideas live. Supermassive stars, dark stars powered partially by dark matter annihilation and other short-lived extreme objects. They would leave behind unique chemical signatures, black hole seeds, and maybe gravitational wave signals. That entire era could be hiding at redshifts beyond 20, out of reach right now. So MOMZ-14 is almost certainly not the first galaxy. It's more like a latecomer in that early crowd, but one that grew unusually fast and turned itself into a bright beacon we can actually see. Behind it in redshift and in time, there is probably a whole hidden ecosystem of more primitive systems that started the process earlier. That's why the right way to think about MOMZ-14 is not as a finish line, but as a signpost. It's a giant blinking marker at the edge of our current map saying, "You're almost at true cosmic dawn, keep going." As JWST gets more deep fields and longer exposures, as we stack more observations, that frontier will move. Future instruments from space and from the ground will push even closer to t equals 0, and what we currently treat as impressive records will turn into intermediate steps. Right now though, MOMZ-14 is the flag planted at the furthest confirmed edge. It shows that the universe wasted no time building compact, bright, chemically active systems. It tells you the story of structure formation starts earlier and ramps up faster than our old pictures admitted. And that brings up the question that makes this whole thing tense. If galaxies like MOMZ-14 exist in such numbers and with such properties this early, do we actually need new physics to explain them? Or can we rescue the picture with better, more aggressive astrophysics inside the same basic cosmological framework? So does MOMZ-14 actually kill our standard picture of the universe? Or is it just telling us our models for how galaxies grow are too conservative? You've probably seen the headlines, JWST breaks cosmology, ΛCDM is dead, new telescope destroys Big Bang model. They spread fast because they sound dramatic. And an object like MOMZ-14, bright, tiny, chemically evolved and sitting only 280 million years after the Big Bang, fits perfectly into that hype. It looks like the kind of thing that should not exist if the old models are right. But if you read the actual research papers instead of the clickbait, the tone is different. Most authors are very careful. They talk about tension with galaxy formation models, not with the core cosmological framework itself. In other words, the problem is not obviously the expansion history or the basic ingredients, dark energy plus cold dark matter. The problem shows up when you ask, given that framework, how quickly do halos form, how much gas falls in, how efficiently does that gas turn into stars, and how hard does feedback push back? So the question becomes, do we really need to throw out the whole cosmology, or do we first push every boring piece of astrophysics as far as it will reasonably go and see if that's enough? Right now, the honest answer from most of the community is, chat with the boring stuff. You already have a long list of adjustable knobs in your galaxy formation recipes. You can raise the star formation efficiency in dense, early halos, meaning a higher fraction of gas turns into stars per unit time. You can tilt the stellar initial mass function so that early star-forming regions produce more massive stars on average, which increases luminosity and enrichment for the same stellar mass. You can weaken the strength of feedback at very high redshift, so that supernovae and stellar winds do not blow out gas as efficiently as they do in the lower redshift calibrations. You can adjust dust formation timescales, letting metals exist without immediately building up thick dust that hides the UV, which matches the very blue continuum of MOMZ-14. You can increase the gas inflow rates along cosmic filaments into high sigma halos, keeping the fuel lines more open than you assumed. All of those are within the system changes. They do not demand a new form of dark matter. They do not require you to alter the basic expansion law of the universe. They just say, maybe early galaxies are more efficient, more top-heavy. Heavy, less feedback limited, and more strongly fed than we thought. That's a big shift, but it stays within the same cosmological box. The rule of thumb in science is always exhaust the simple, less dramatic explanations before you claim a revolution. So when do you start to suspect that turning knobs is not enough and that something more radical might be going on? If future Webb data show not just a handful but thousands of MUMSY-14-like galaxies, or even more extreme ones at similar or higher redshifts, and if their number densities and properties remain wildly inconsistent with any reasonable tuning of the existing models, then you have a stronger case. At some point, if every version of more efficient star formation, weaker feedback, and slightly different initial mass function still fails to match the data, you are forced to ask if the underlying assumptions about structure growth or initial conditions are wrong. That's when more speculative ideas start to enter the discussion. Maybe the initial density fluctuations were not purely Gaussian. Having more weight in the high sigma tail could make early massive halos more common. Maybe there was an early dark energy episode that briefly changed the expansion rate and structure growth before fading away. Maybe there are new feedback channels we have not modelled properly, where energy couples to gas in very different ways at high redshift. MUMSY-14 by itself doesn't force you to adopt any of those ideas yet, but it pushes the door open. It says, if you keep seeing more of me and my cousins, tweaking the old recipes may not be enough. There is another constraint you cannot ignore: other cosmological probes. The same ΛCDM framework that seems under pressure from early bright galaxies is also what matches the cosmic microwave background patterns, baryon acoustic oscillations, and supernova distance measurements pretty well. Those data sets are independent and cover different eras and scales. Any new physics you bring in to explain MUMSY-14 has to survive all of those tests too. You cannot just say, let's change the expansion history so structures form earlier, if that change wrecks the fit to the microwave background or ruins the agreement with large-scale galaxy clustering today. You cannot just declare dark matter is warm, if that makes it impossible to form enough small-scale structure that we already observe. Any proposed fix has to pass a full gauntlet of data, not just one surprising galaxy. That's exactly what makes this kind of problem interesting instead of trivial. You're not allowed to fix one number and break 5 others. So the constructive way to talk about this is not cosmology is broken. It's more accurate to say cosmology is now in high precision mode, and MUMSY-14 is one of the first real stress tests at percent level detail. Before Webb, a lot of early universe galaxy work was limited by small samples and shallow data. You could hide a lot of model uncertainty under big error bars. Now you have objects with measured redshifts above 14, star formation rates, chemical abundances, sizes, and number densities that you can actually compare to detailed predictions. When those predictions are off by factors of 10 or 100, you're not in the noise anymore. You're in a regime where your prescriptions are meaningfully wrong. This is exactly where scientific revolutions either start or where models get much sharper. You push the existing framework as hard as you can, adjust every parameter within reason, and if it still fails, that failure is what points you to new physics. If it does succeed after serious tuning, then MUMSY-14 has still done its job. It forced you to understand baryonic physics in the early universe far better than before. Either way, this little compact galaxy at redshift 14 is not just an oddity. It's a calibration point at the edge of the observable timeline, a real object that tells you where the simple stories fail and where the detailed, high-precision picture has to take over. And that leads to the next step in the story. Now that we know these extreme galaxies are out there and matter this much, what are the next generation tools, space telescopes, deep surveys, and giant ground-based observatories going to do to map this era properly? And how far can we realistically push the frontier beyond MUMSY-14 in the coming decade? So once you have found something like MUMSY-14, what do you actually do next? stop at one record and celebrate, or start rebuilding the whole map of the early universe around it. James Webb is still early in its mission. What we've seen so far is based on a limited number of deep fields and a lot of relatively short exposures by Webb standards. The straightforward way to push further is simple: stare longer in more places. When you increase exposure time, your sensitivity improves roughly with the square root of that time. So if you push an exposure from, say, 10 hours to 40 hours on the same patch of sky, you go about 2 times deeper in flux. That's enough to turn galaxies that are currently invisible into clear detections. Right now, we're mostly seeing the celebrities, objects like MUMZ-14 that are unusually bright for their epoch. Longer exposures and more deep filters will reveal the background chorus, the smaller, fainter galaxies that are actually doing most of the population-level work. Those faint systems are crucial if you want to know how reionization really unfolded, and how common normal galaxies were versus extreme ones. So the plan with Webb is not just find one more record breaker, it's fill in the entire luminosity function, meaning how many galaxies you get at each brightness at each redshift. That requires a grid of deep fields across different parts of the sky, so you aren't fooled by one lucky overdense region, and a lot of cumulative exposure time, hundreds or thousands of hours stacked carefully. But deep images are only half the story. Right now, detailed NIRSpec spectra like the one for MUMZ-14 are precious and rare. Each one takes serious telescope time, and you don't want to waste that on objects that might turn out to be low redshift interlopers. The next phase is scaling that up with multi-object spectroscopy. NIRSpec has a microshutter array that can open thousands of tiny shutters and take spectra of many galaxies at once in the same field of view. Future programs will lean heavily on that. Instead of doing one galaxy at a time, you target hundreds of high redshift candidates in a single pointing. That will give you a statistical sample, not just isolated cases. You'll be able to ask questions like, out of, say, 500 galaxies at redshift around 10 to 15, how many show nitrogen-rich chemistry like MUMZ-14? How many are dust-poor? How many are compact starbursts versus more extended disks? And how do those fractions change with redshift? That is how you move from this is a weird object to this is a known population with measured properties. Webb is not doing this alone. The Nancy Grace Roman Space Telescope is coming, and it completely changes the geometry of the problem. Roman will have Hubble-class resolution, sharp images measured in tenths of an arc-second, but its field of view in the near-infrared will be about 100 times larger than Hubble's. That means instead of tiny pencil beam surveys that cover areas comparable to a small fraction of the Moon's apparent diameter, you can map huge patches of sky with Hubble-like sharpness. Roman will be able to find thousands of MUMZ-14-like galaxies and many fainter ones across enormous areas. It won't go as deep as Webb on a single object, but it will go very wide with high quality. The natural workflow becomes a two-step. Roman does the wide field discovery. It finds candidates, builds huge catalogues of high redshift objects, and maps the large-scale structure of the early universe. Then Webb goes back in, zooms on the most interesting targets, and does the deep, high-resolution imaging and spectroscopy. Roman shows you where the rare beasts live. Webb dissects them. On the ground, the next players are the 30-meter class telescopes, the extremely large telescope in Chile, and other giants in the same class. With mirrors 30 meters across or more, plus adaptive optics to correct for the atmosphere, these telescopes will resolve very fine details in faint galaxies, especially at slightly lower redshifts where key spectral lines shift into their optimal bands. For MUMZ-14-like systems and their lower redshift cousins, those ground-based giants will probe rest frame optical light, not just the UV we see with Webb, but the longer wavelengths that trace older stars and give more accurate stellar mass estimates. They can try to pick up nebular lines like hydrogen alpha, which is a powerful tracer of star formation, in analog systems at redshifts where that line falls into the near-infrared from the ground. By studying those somewhat closer cousins in extreme detail, we calibrate the models we use for the very high redshift galaxies where we only have UV. You learn, for example, how UV luminosity really tracks star formation rate and stellar mass in systems with similar conditions, then apply that calibration back to MUMZ14 and friends. All of this builds towards a specific goal, pushing beyond our MUMZ14 into redshifts of 20 and maybe even 30, where the very first stars and star clusters turn on. To reach that regime, you don't just need more powerful hardware, you need smarter strategies. One strategy is gravitational lensing, using massive galaxy clusters as natural telescopes. Their gravity bends and magnifies light from background galaxies, effectively boosting Webb sensitivity. That lets you see fainter and more distant objects than you could in blank fields. Another is optimizing filter sets and survey design specifically for ultra-high redshift detection, making sure you have the right wavelength coverage to catch extreme dropouts at Z above 20. You also lean on statistical tricks, stacking multiple faint detections, cross-matching with predicted positions of ionized bubbles in future 21cm maps, and doing clever selections that maximize the chance of catching the earliest systems. The idea is to slowly push the confirmed frontier of galaxy formation backward in time, step by step, while keeping the measurements solid. MUMZ14 is the proof of concept that this frontier is reachable in the first place. It shows that Webb's instruments, survey strategies, and analysis pipelines can, in practice, pull out a real galaxy at redshift 14 with a secure spectrum and detailed physical properties. That's not a guess anymore, it's a demonstrated capability. Now the question shifts from, can we reach this era at all, to how densely can we map it, and how much further can we push? And as that map fills in, the implications loop back to you directly. If the universe built bright, chemically complex galaxies this fast, how does that change the story of where you fit in the cosmic timeline, and how early the raw material for you actually started its journey? How do you fit into a universe that clearly moves way faster than the story you grew up with? Most popular timelines make the early universe sound gentle and slow. Big Bang, long dark ages. Then the first stars, then small galaxies, then eventually big complex ones, and only much later does anything interesting really happen. That picture lets you relax. It feels like the universe took billions of years to warm up before it did anything serious. MUMZ14 basically walks into that story and throws it out. This little brutal object is telling you that massive bright systems are already roaring by 280 million years after the Big Bang. Not just a few lonely stars, but compact galaxies with intense star formation, weird chemistry, and serious impact on their surroundings. So instead of a sleepy ramp-up, the actual sequence looks more like the universe cools, structure growth starts, and then very quickly you get dense halos, extreme starbursts, nitrogen-rich gas, and ionized bubbles. The gap between almost no structure and hyperactive galaxies is a lot shorter than the mental image most people carry around. The story of how we got here has to be updated. It's not Big Bang, then a long pause, then galaxies, then us. It's Big Bang. And within a few 100 million years, regions like MUMZ14 are already building the ingredients and carving the radiation background that future galaxies, stars, and planets will inherit. So if the old picture is too slow, how fast is the real one actually running? Look at the numbers. The universe starts as a hot plasma of mostly hydrogen and helium. Recombination happens, the cosmic microwave background is released, and the gas cools and starts to fall into dark matter halos. By the time you're at 280 million years, less than 0.3 billion out of 13.8 billion, you already have MUMZ14, a compact, nitrogen-rich, dust-poor, starburst galaxy, packed into a region only about 240 light-years across. To compare, think about Earth's fossil record. The gap between the first complex animals in the Cambrian, roughly 540 million years ago, and humans now, is around 540 million years. That's almost double the entire time between the Big Bang and MUMZ14. In less than that span, the universe goes from no stars, no galaxies, just hot gas and dark matter, to multiple generations of massive stars have formed and died, heavy elements exist and galaxies are reshaping their surroundings. So cosmic structure doesn't ease its way into complexity, it rushes into it. Regions like MOMZ14 show that gravity plus gas physics go from almost nothing to fully chaotic, high-intensity star factory in a fraction of a billion years. On the timeline of the universe, that's a fast transition. If things ramp up that quickly, what does that say about the material you're made of? The nitrogen and carbon we see in MOMZ14's spectrum are chemically the same elements in your DNA, in your proteins, in your blood. The atoms are not similar, they're literally the same kind of atoms. There's a simple path you can trace. Supermassive and massive stars and galaxies like MOMZ14 fuse hydrogen and helium into heavier elements, including carbon and nitrogen. Those stars die. Throw that enriched material into the surrounding gas, and that gas later cools and condenses into new generations of stars. Some of those later stars have disks of gas and dust around them. In those disks, dust grains stick together, grow, and eventually form planets. Some of those planets end up in the right temperature ranges, with the right chemistry for life to form. Billions of years later on one of those planets, a species appears that can build telescopes and point them back toward MOMZ14. So MOMZ14 is not just a random distant object, it's an early factory making the same chemical ingredients that, after a long chain of steps, became you. When you see that nitrogen bump in its spectrum, you're essentially watching a very early chapter of how your atoms got rearranged into something that can ask questions. If the universe can build complex galaxies this fast, what does that say about how we should tell its story? Lots of people imagine the universe like a slow novel, long exposition, careful build-up, then eventually action. MOMZ14 doesn't fit that format. A better way to see it is more like a cold open in a TV episode. The universe doesn't spend the first few billion years explaining itself. It starts with explosively bright, compact galaxies already running hot, already affecting their surroundings, already producing heavy elements and ultraviolet radiation. By the time you could put a title card on the universe, something like 13.8 billion years later, a lot has already happened. Reionization is underway, complex chemistry is established in pockets, dense halos are merging, and the cosmic web is well formed on many scales. The stage is crowded long before the part of the story that humans tend to focus on, the formation of galaxies like the Milky Way and planets like Earth. So where do you actually enter this script, if not at the comfortable point of Earth forms 4.5 billion years ago? The way people usually think is, my story starts when Earth forms, or maybe when life starts on Earth. That's understandable, but it's way too narrow. If you trace your atoms back, your real story starts when those atoms first stopped being just hydrogen and helium. That shift from simple elements to heavier ones like carbon and nitrogen is already happening in galaxies like MOMZ14 at redshift around 14. Some of the very first metal-enriched gas clouds are forming stars there. The future material for planets, for biology, for everything more complex than hydrogen and helium is being set up in that era. So the more accurate way to say it is, your story doesn't start 4.5 billion years ago. It starts over 13 billion years ago in objects like MOMZ14 and in whatever came before it at even higher redshift. That's where your atoms were first forged into something more interesting than simple gas. That's where the first steps toward you were taken, even though the universe had no idea where that path was heading. Once you look at MOMZ14 that way, the tension is obvious. If a single tiny galaxy that far back can force us to rewrite the early chapters of our origin story, what happens when we add hundreds more like it? And how much of our comfortable cosmology is going to survive that rewrite intact? So what does MOMZ14 actually do to our picture of the universe when you put all the pieces on the table and look at it straight? You're dealing with a galaxy only about 240 light-years wide, sitting 280 million years after the Big Bang, at a redshift of 14.44. It's dust poor, which is why its light is so clean and blue. It's nitrogen rich, which means at least one earlier generation of massive or even supermassive stars has already lived and died there. And it's forming stars at an intense rock rate inside a volume so small that you could cross it at 1% of light speed in just tens of thousands of years. By every metric, it is brighter and more evolved than our pre-JWST models said it had any right to be at that time. Its light has been travelling for about 13.5 billion years to reach us, but because the universe has expanded underneath that beam, the proper distance to MOMZ-14 today is not 13.5 billion light-years, it's over 30 billion light-years, roughly 33.8 billion. In distance units, that's on the order of 3 times 10 to the power of 23 kilometres, or about 1.9 times 10 to the power of 23 miles, between us and a compact object that existed when the universe was at roughly 2% of its current age. So when you say this galaxy shouldn't exist, what you really mean is, this galaxy doesn't fit the comfortable middle-of-the-road version of early structure formation we got used to before Webb. It squeezes maximum complexity into minimum time, minimum size, and maximum distance all at once, and it does not walk away quietly. It leaves a pile of questions sitting there, demanding answers. How did its dark matter halo assemble that much mass so fast? Building something like 10 to the power of 9 to 10 to the power of 10 solar masses of invisible matter in only 280 million years. Why is nitrogen already so enhanced compared to carbon, echoing chemical patterns we only expected to see in special fossil environments like ancient globular clusters near the Milky Way? How long has this starburst phase been going on, and how many burst and pause cycles has it already lived through? How many more galaxies like MOMZ-14 are quietly hiding in Webb's imaging catalogues right now, tagged as high redshift candidates but still waiting for spectroscopic confirmation? Are we looking at 1 or 2 edge cases, or the bright end of a huge, previously invisible population that forces us to rebuild our models from the ground up? Each of those questions is a small crack in the old tidy picture. None of them by themselves kill ΛCDM or the Big Bang. But together they say, your default, slow, gentle early universe story is wrong in important ways. The good news, or the bad news, depending on your point of view, is that you're not going to have to wait very long to see where this goes. Over the next 5 to 10 years, James Webb, the Nancy Grace Roman Space Telescope, and 30-metre class ground telescopes like the ELT are going to absolutely flood this part of the timeline with data. Webb will keep pushing deeper with longer exposures and more fields, turning up fainter and fainter galaxies at redshifts 10, 12, 14 and beyond. NIRSpec will move from one-off spectra to multi-object campaigns, grabbing hundreds of high redshift spectra in a single shot, mapping chemical patterns, sizes, and star formation rates as a function of redshift instead of as isolated anecdotes. Roman will sweep huge areas of sky with Hubble-like sharpness in the near-infrared, finding thousands of MOMZ-14-like galaxies and their quieter cousins. That will give us real statistics. How common are these compact nitrogen-rich starbursts, and how clustered are they in the cosmic web? Then Webb and the big ground-based telescopes will dive in on the most interesting subsets and tear them apart in detail. Either the models adapt by dialing up early star formation efficiency, changing feedback rules, revising chemical enrichment channels, maybe adding supermassive stars as standard ingredients. Or the data push so hard that some deeper rethink becomes unavoidable. Either way, you're living through a once-in-a-century reshaping of the cosmic origin story. This is not a minor patch, it's a whole new regime of precision. So here's the final challenge I want in your head the next time you see a headline about a new most distant galaxy. MOMZ-14 holds the record now, but records are invitations, not endpoints. Somewhere out there, at redshifts above 15, maybe above 20, there is already a galaxy whose light is buried in the noise of current images, not yet cleanly separated, not yet given a name and a redshift. When a Webb team eventually drops a paper saying, we've confirmed a galaxy at Z equals 1518 or even 20, I want you to instantly feel why that matters. You'll know that each jump is not just a new high score. It's a direct hit on how fast the universe can assemble mass, how quickly it can form stars, how early it can enrich gas, and how soon it can start clearing the hydrogen fog. Every step to higher redshift is another test of whether MOMZ14 was an outlier or the first of a whole family of extreme objects. And underneath all of that, there's the bigger perspective you can't lose. MOMZ14 does not mark the edge of the universe. It marks the edge of what we can currently confirm. In metric terms, we've mapped just a sliver of a cosmos that spans roughly 10 to the power of 26 meters, 100 billion trillion kilometers on large scales. In ordinary terms, we're still standing on the beach looking out over the water, and MOMZ14 is just the first real wave that tells you there's a deep ocean beyond what your eyes can see. Your cosmic address just got weirder, not because the universe broke, but because the part of the map labelled "Here be early galaxies" turned out to be full of bright, compact, chemically complex systems that woke up much faster than anyone expected. And the real question now is simple and sharp. As we push further into that ocean, do we find a universe that just runs hotter and faster than we thought? Or one that forces us to rewrite the rules themselves? This video's for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.